So here we have a simulation software that will allow me to perform a demonstration of the experiment involving the stopping potential. We have a light source with a variable wavelength and intensity. And of course, a photocell with a metal target here that can be changed amongst different materials. I will stick with sodium for the time being. Okay, so let's start with red at a wavelength of 700 nanometers. I am setting the intensity of light to 50%. You can see that no electrons are ejected from the metal surface. And this is because the frequency of light is not sufficiently high, and thus the photons are not sufficiently energetic to knock off electrons. Note that the light intensity has no effect on this. In fact, if I increase the intensity, say to 100%, we still get no photoelectrons. As we start decreasing the wavelength, at a certain point, we exceed the threshold frequency, and we start observing the photoelectric effect. You may see the electrons reaching the other terminal of the photocell. The current is still too low to register here. But as we get more electrons, we start registering a current here. I will start this experiment with violet at a wavelength of 400 nanometers. Okay, so I will apply now a reverse voltage, which is a negative voltage, which will make this plate I'm showing here negative, thus repelling electrons or slowing them down. As it is, some electrons are still managing to get through. But if I keep increasing the voltage in a negative sense, at a certain point we strike a current of 0. This happens at exactly minus 0.72. If I go minus 0.71, I should still detect a small current. So minus 0.72, that is the exact value at which we get no current. So this is the stopping potential or stopping voltage when the wavelength is 400 nanometers. And I will take note of these two data points in my table. Now, I will decrease the wavelength to 350 nanometers. We are now in the ultraviolet region. Now the electrons emitted are more energetic, so we start getting again a current. To stop it, we need to increase the voltage. Okay, so we are at minus 1.20 volts now. In fact, if I go 1.17, we get a current. Minus 1.18, we get no current. So this is the exact value of stopping voltage at a wavelength of 350 nanometers. And again, I take note of this. And I will continue to decrease the wavelength in steps of 50 nanometers till I get a table of results with at least 5 data points. And I will show it to you in a moment. Okay, so here you may note the values of lambda in nanometers and the values obtained for the stopping potential. I will explain to you why I've calculated values of 1 on lambda in a moment. Okay, I will get back to the graph in a moment. I will show you first some theory. We start with Einstein's photoelectric equation. And I'm going to substitute V on lambda instead of the frequency, since our experiment was in terms of wavelength rather than frequency. And then I am arranging the equation by grouping the constants appropriately. Planck's constant, speed of light, electron charge, these are all constants, which leaves the variable 1 on lambda and minus W on here as the intercept. So this equation is showing us that we need to plot the stopping voltage on the y-axis against the reciprocal of the wavelength on the x-axis. And that explains why we need this extra column here. And this is the graph which we are talking about, of stopping potential against the reciprocal of the wavelength. We are still in nanometers here. I am also showing this straight line equation, y is equal to mx plus c, which is the equation of the best straight line we got here, already with the values shown for the gradient and the y-intercept. We will use these in a moment. Now, from the equation, the gradient is equal to hv on E. And hence, we can determine Planck's constant as shown here. All I've done is to make h subject of the formula and then substituting with the value of the gradient. I've taken care to adjust the units here, since we were still in nanometers. This is the electron charge, and this is the speed of light. And here we got the value for Planck's constant, which is fairly close to the actual value quoted in books. Similarly, we can say that the y-intercept is equal to minus W on E. Don't forget that W stands for work function. Okay, you can see it over here as well. The y-intercept is equal to minus W on E. Hence, we can also determine the work function for sodium. Again, all I've done was to substitute with the value for the y-intercept, which is a value in volts, which are equivalent to joules per coulomb, multiplied by the electron charge, which is in coulombs, So that leaves a value in joules. This is the work function. We can also convert this value into electron volts by dividing by this number. So we can calculate the work function either in joules or in electron volts. So the work function for sodium is 2.42 electron volts. This brings us to the end of this session about the photoelectric effect. I hope you liked it. Bye.